All right. Good evening, everyone. For today, we'll be discussing our second module, and the module is all about concept of computer architecture and organization. And the topics that we're about to cover are concept of computer architecture and computer organization, contemporary computer architecture, so the von Neumann architecture plus the interrupts, including number systems, a review if time allowed, but I understand that your other subjects already covered the number systems. So what is computer architecture? So computer architecture refers to the design and structure of a computer system, including its components and the way they interact. It involves defining the organization, functionality, and connectivity of the various hardware elements, such as the central processing unit or CPU, memory, input and output devices, and the system's overall structure. In simpler terms, computer architecture outlines the blueprint or framework that dictates how a computer's hardware components work together to execute instructions, process data, and perform tasks. So, what is computer organization? Computer organization, on the other hand, refers to the arrangement and design of the internal components of a computer system. It focuses on how different hardware elements, such as the central processing unit or the CPU, memory, input and output devices, and the control unit are interconnected and work together to execute instructions. So, in simpler terms, computer organization deals with the way a computer's internal components are structured and how they collaborate to perform tasks and process information. It is more concerned with the low-level details of hardware implementation and the coordination between various components to ensure the effective operation of the computer system. In essence, computer architecture sets the broader design goals and principles, while computer organization delves into the implementation details necessary to realize these goals. Architecture is more about the what and why of a computer system, defining its overall structure and functionality. Organization is more about the how, addressing the practical details of how the components are arranged and interconnected to execute instructions and process the data efficiently. So let's now talk about the contemporary computer architecture, the von Neumann architecture. Contemporary computer architecture, at its core, follows the von Neumann architecture, a foundational design where instructions and data share the same memory. In addition to this structure, contemporary systems incorporate the concept of interrupts. Interrupts are signals that temporarily halt the normal execution of a program to handle specific events, allowing the computer to respond to external stimuli such as input from devices or requests for attention. This combination of von Neumann architecture and interrupts enhances the flexibility and responsiveness of modern computers by enabling them to efficiently manage multiple tasks and external events. So this is the von Neumann architecture. So as you can see, the von Neumann architecture contains the central processing unit. So we have the arithmetic logic unit and the program control unit interconnected with the input-output equipment and the main memory. Von Neumann architecture is a computer design model that describes a processing unit, memory, and input-output devices, all connected by a bus. In this architecture, both data and instructions are stored in the same memory space, and the processing unit fetches and executes instructions sequentially. It is named after mathematician and physicist John von Neumann, who proposed this fundamental concept in the 1940s. Von Neumann architecture forms the basis for most general-purpose computers, emphasizing the sequential execution of instructions and the shared use of memory for both data and program storage. The IAS computer, designed by John von Neumann and his colleagues at the Institute for Advanced Study in the late 1940s, is considered a prototype for modern computers. It features the stored program concept, where both program instructions and data are stored in the same memory. The von Neumann architecture, as demonstrated by the IAS computer, allows for flexibility in programming and sequential execution of instructions by the Central Processing Unit or CPU. The memory of the IAS or the Institute for Advanced Study computer refers to the storage component where both program instructions and data are stored for processing. In the context of the IAS computer and the von Neumann architecture it utilized, memory is a unified space that holds the instructions that guide the computer's operations and the data on which these instructions operate. This stored program concept allows for greater flexibility and efficiency in computing, as instructions can be modified and data can be processed sequentially by the central processing unit or CPU. The memory in the IAS computer played a crucial role in implementing the foundational principles of modern computer architecture. The instruction set of the IAS or the Institute for Advanced Study Computer refers to the specific set of commands or operations that the computer's central processing unit can execute. In simpler terms, it encompasses the list of tasks or operations that the computer can understand and perform. The instruction set is a crucial aspect of the computer's architecture, as it defines the capabilities and functionalities available for programming. Users interact with the computer by providing instructions from this predefined set, allowing them to perform various tasks and operations using the machine. So I'll be discussing to you briefly the 21 instructions that discusses the data transfer between memory and registers or between the two registers, the unconditional branch, conditional branch, arithmetic, and then the address modify. The instruction set of the IAS computer includes various types of instructions, each serving a specific purpose. Arithmetic instructions, so these are the instructions involve mathematical operations such as addition, subtraction, multiplication, and division. They manipulate numerical data stored in the computer's memory. Logical operations perform logical operations such as AND, OR, and NOT. They are used for making decisions and controlling the flow of the program based on certain conditions. On the other hand, data transfer instructions move data between the CPU registers and memory. They are essential for loading values into the CPU, saving results, and managing data storage. Control transfer instructions alter the sequence of program execution. They include branch and jump instructions that enable the program to skip or repeat certain sections based on conditions. Input-output instructions manage the communication between the computer and external devices. They facilitate the transfer of data between the CPU and peripherals, such as storage devices or input devices. So these common instruction types collectively form the instruction set architecture of the IAS computer. Programmers use combinations of these instructions to create sequences that perform specific tasks and operations on the computer. Registers in the context of the IAS computer are small, fast storage locations within the central processing unit. They hold temporary data and are used for various purposes during the execution of instructions. In simpler terms, registers in the IAS computer serve as quick access, high-speed memory locations that the CPU uses to store and manipulate data efficiently during its operations. The IAS architecture typically includes registers for tasks like holding operands for arithmetic operations, storing memory addresses, and facilitating the flow of data within the processor. So here we have the memory buffer register, the memory address register, instruction buffer register, program counter, accumulator, and multiplier quotient. So some of which are already discussed in the SUP1, SUP2, and SUP3 computers. The operation of the IAS computer involves sequential execution of instructions stored in memory. In simpler terms, the CPU fetches instructions from memory, decodes them to understand the operation to be performed, executes the operation, and stores the result. This process continues in a cycle with the CPU moving through each instruction in sequence. The IAS computer's architecture based on the von Neumann model allows for the stored program concept where both instructions and data are stored in the same memory space, contributing to the flexibility and versatility of the computer's operations. So here's the simple operation of the IAS from the instruction cycle down to the fetching from OP code to the instruction register, then address to memory address register, and then execute. So let's now discuss about the interrupts. Interrupts in the context of computing refers to signals or events that temporarily halt the normal execution of a program to shift the attention of the central processing unit to address a specific condition or event. In simpler terms, interrupts are mechanisms that allow a computer to respond promptly to external stimuli such as signals from input devices, requests for attention, or other events that require immediate processing. When an interrupt occurs, the CPU temporarily stops its current activities, saves its states, and jumps to a predefined routine to handle the interrupt. This enables computers to efficiently manage multiple tasks and respond swiftly to external events while maintaining overall system functionality. Common classes of interrupts refer to categories or types of events that can trigger the interruption of the normal execution of a computer program. In simpler terms, these are broad groups of interrupt signals that prompt the central processing unit to temporarily suspend its current task and address specific situations. So these classes of interrupts help the computer system efficiently handle various events, ensuring responses or responsiveness and proper functioning in the face of external stimuli or exceptional conditions. Program flow of control without interrupts refers to the sequential and uninterrupted execution of instructions in a computer program. In simpler terms, when a program runs without interruptions, each instruction is executed one after the other in a linear fashion. The program proceeds through its code, completing each task or operation before moving on to the next. Without interrupts, the program does not pause to handle external events or conditions, but instead follows a straightforward and continuous path of execution. This type of flow is characteristic of simple, linear program structures where tasks are performed in a predetermined order without interruption. Program control without interrupts refers to the linear sequence of instructions in a computer program without interruptions for external events. In simpler terms, the program proceeds through its instructions in a predetermined order and each operation is completed before moving on to the next. Without interrupts, the control flow remains strictly governed by the program's structure. With no interruptions or deviations due to external stimuli, the timing of operations follows a predictable pattern, allowing the program to execute instructions without interruption from events such as input signals or hardware triggers. So why do we use interrupts? So with interrupts, the processor can be engaged in executing other instructions while an input-output operation is in progress. So basically, it's for improvement, processing efficiency, and concurrency. Short input-output wait refers to a brief period during the execution of a program when the CPU temporarily pauses to wait for input or output operations to complete. In simpler terms, when a program encounters a situation where it needs to interact with external devices, such as reading from or writing to a disk, the CPU may briefly pause its current activities until the input-output operation is finished. This short pause, known as short I/O wait, allows the CPU to efficiently manage its time by not actively processing instructions during the relatively quick input-output operation. Program control and timing with interrupts involving short input-output wait refers to a situation where a computer program, while executing instructions, may be interrupted briefly to wait for input or output operations to complete. In simpler terms, interruptions known as interrupts can occur during the program's execution to handle external events such as input or output requests. The program's control, flow, and timing are affected by these interrupts, causing short pauses, short input-output wait to efficiently manage input and output operations. This interruption mechanism allows the program to respond promptly to external events without the need for the CPU to continuously wait during lengthy input and output operations. Long input and output wait refers to a prolonged period during the execution of a program when the CPU is idle, waiting for an input or output operation to be completed. In simpler terms, when a program initiates a time-consuming input and output task, the CPU may remain inactive for an extended duration until the external operation, such as reading or writing data to a storage device, is finished. During this long input and output wait, the CPU is not actively processing instructions, and the program's execution is temporarily suspended until the input and output operation concludes. Program control flow and timing with interrupts involving long input and output wait refers to a situation where a computer program during execution experiences a prolonged interruption or pause due to an extended input and output operation. In simpler terms, interrupts can occur while program is running to handle external events such as time-consuming input or output tasks. During a long input and output wait, the program is temporarily halted, allowing the CPU to remain idle for an extended period until the lengthier input and output operation is completed. This mechanism enables the program to manage external events efficiently even when they require more time to execute. As per the summary, with the use of interrupts, concurrent execution of user program and I/O operation is made possible. So improve CPU processing efficiency. Transfer of control via interrupts refers to the process in which the normal execution flow of a program is temporarily halted, and the control is transferred to a specific routine or handler to address a particular event. In simpler terms, when an interrupt occurs triggered by external event like a hardware signal or software-generated event, the program temporarily stops its current activities. Instead, the control is transferred to a predefined section of code known as an interrupt service routine or the ISR, which handles the interrupt. Once the ISR completes its task, the program returns to its previous state, resuming normal execution. This mechanism allows computers to efficiently respond to external events without constantly monitoring for them, enhancing overall system responsiveness. Multiple interrupts refer to a scenario where a computer system can handle more than one interrupt at a time. In simpler terms, if multiple events occur simultaneously or in a rapid succession, the system is capable of managing and prioritizing these interrupts and concurrently. Each interrupt may have its own interrupt, service routine or the ISR, and the system decides which ISR to execute based on factors such as priority levels or the type of event. The ability to handle multiple interrupts allows a computer to efficiently respond to various external events and maintain responsiveness in a multitasking or multi-input environment. Dealing with multiple interrupts involves managing and prioritizing concurrent interrupt requests in a computer system. In simpler terms, we have the interrupt prioritization that assign priorities to different types of interrupts based on their urgency or importance, handle higher priority interrupts first to ensure critical tasks are addressed promptly. Interrupt masking temporarily disable or mask lower priority interrupts while servicing higher priority ones. Prevents lower priority interrupts from interfering during critical operations. Interrupt vector table uses an interrupt vector table to map each interrupt type to its corresponding interrupt service routine or the ISR. The system consults this table to determine which ISR to execute for a specific interrupt. Context switching save the current state of the CPU, including registers and program counter, before handling an interrupt. Allows for a seamless transition back to the interrupted task once the ISR is complete. In terms of the nested interrupts, some systems support nested interrupts, allowing the CPU to handle a higher priority interrupt even while servicing a lower priority one. Requires careful management to avoid conflicts and ensure proper execution. By implementing these strategies, a computer system can effectively manage and respond to multiple interrupts, ensuring that critical tasks are handled promptly and in an organized manner. So, can an interrupt be interrupted while it is being processed? No. Due to sequential interrupt processing? Yes. Which interrupt should the CPU service? Priorities and nested interrupt processing. Sequential interrupt processing refers to the method of handling interrupts in a sequential or one at a time fashion. In simpler terms, when an interrupt occurs in a computer system, it is processed in a step by step manner, one after the other. The system addresses and resolves each interrupt in the order they are received, without overlapping or concurrent execution. This approach ensures that interrupts are handled in a predictable and orderly sequence, which may simplify the management of shared resources and prevent conflicts between interrupt service routines. So here's the advantages and disadvantages of the sequential interrupt processing. For the advantages, all interrupts are handled in strict sequential order. And for the disadvantage, without considering relative priority or time critical needs. Nested interrupt processing is a method of handling interrupts in a computer system where a higher priority interrupt can be serviced even while a lower priority interrupt is being processed. In simpler terms, if a lower priority interrupt occurs while the system is already handling a higher priority interrupt, the system temporarily interrupts the lower priority process to address the more critical event. This allows for a level of prioritization and responsiveness, ensuring that important tasks are handled promptly, even if less critical interrupts occur concurrently. So here's the nested interrupt processing. A system has three input and output devices, a printer with priority 2, a disk with priority 4, and a communication line with priority 5. So as you can see, we have here illustration showing the increase in terms of priority. Nested interrupt processing in the context of handling multiple interrupts involves a time sequence where interrupts of different priorities are managed in a nested or hierarchical manner. In simpler terms, in terms of the time sequence, when multiple interrupts occur at different times, the system processes them based on their priority levels. Higher priority interrupts are handled immediately, and the system may interrupt a lower priority interrupt to service the higher priority one. Nested interrupts. If a lower priority interrupt is being processed and a higher priority interrupt occurs, the system can temporarily suspend the lower priority processing to address the more critical event. This nesting capability allows for efficient handling of multiple interrupts, ensuring that the most urgent tasks are addressed promptly. Example, for instance, if the system is executing a routine in response to a lower priority interrupt and a higher priority interrupt is triggered, the system temporarily pauses the lower priority routine, handles the higher priority interrupt, and then resumes the lower priority processing. In summary, nested interrupt processing involves a time-ordered sequence where interrupts are handled based on their priority levels with the ability to interrupt lower priority routines to address more critical events. So here's the advantages and disadvantages of the nested interrupt processing. As per the advantage, taking into account relative priority or time critical needs, and disadvantage, complex, defining priorities and saving information. As per the next topic, we'll be discussing about the concept of computer function and structure. For the function computer view, the basic functions. For the program view, the instruction cycle. And as per the structure, hierarchical system structure, interconnection structures that includes the bus and the multiple bus. Thank you very much.